For months, scientists monitoring Oregon's underwater volcano have watched signals climb toward a critical threshold. The seafloor is swelling like a balloon ready to burst. Magma chambers are filling at rates faster than previous eruption cycles. And this isn't just another volcanic eruption. What's happening 480 kilometers off Oregon's coast has captured the attention of volcanologists worldwide. This underwater giant, while posing no direct threat to shore, offers rare opportunities to observe volcanic processes in real time. Why are researchers watching so closely? What makes this volcano scientifically invaluable despite its remote location? And what can it teach us about forecasting eruptions at more dangerous volcanoes? Axial Seamount rises from the ocean floor like a sleeping colossus. Its summit sits 1,400 meters beneath the Pacific surface, invisible to anyone standing on Oregon's beaches. The caldera spans 3 kilometers wide, scarred by fractures and steaming vents that leak superheated water into the frigid deep. This is no ordinary volcano. Axial sits directly atop the Juan de Fuca Ridge, where 2 tectonic plates are tearing apart. New ocean crust forms here continuously, fed by a relentless upwelling of magma from Earth's mantle. The volcano has erupted 3 times in the last 30 years alone, making it the most active submarine volcano in the entire Pacific Northwest. But this time, something is different. When volcanoes erupt underwater, the dynamics differ dramatically from land-based events. At axial's depth, immense water pressure suppresses explosive behavior, but the interactions between magma and seawater create unique phenomena. Lava flows can reshape vast areas of seafloor in hours, and hydrothermal systems undergo radical transformations. Yet, for those on shore, axial poses little direct threat. Past eruptions have been contained entirely underwater, with no surface effects detectable even by ships directly overhead. But what makes this volcano scientifically crucial is its potential to reveal patterns that could apply to more dangerous systems. Every data point gathered here adds to understanding of how volcanoes behave before they erupt. What scientists are seeing now matches precursors that appeared before major eruptions. The signals arrive with intensity and timing that suggest the volcano's behavior may be evolving. Researchers tracking these patterns note changes in inflation rates and seismic activity that differ from past cycles. The volcano appears to be approaching a familiar threshold, but the path looks different. Stretching from Oregon's coast to the volcano's summit, a web of fiber optic cables carries data at the speed of light. The Ocean Observatory's initiative's regional cabled array represents the most advanced volcano monitoring system ever constructed. Over 900 kilometers of cable connect 150 instruments directly to shore. Every tremor registers instantly. Pressure sensors detect seafloor movements smaller than a sheet of paper. Chemical analyzers sample hydrothermal vent fluids in real time, tracking changes in gas composition minute by minute. Underwater cameras stream live video from the caldera floor, revealing fissures that open overnight. Seismometers record every crack and rumble as rock fractures deep below. William Chadwick, a research associate at Oregon State University's Hatfield Marine Center, leads the monitoring effort. His team analyzes the constant flow of data, tracking changes that reveal the volcano's internal state. Bottom pressure recorders measure vertical deformation with millimeter precision. Chemical sensors track helium-3 signatures in vent emissions, a telltale sign of fresh magma rising from the mantle. The instruments never sleep. This system has captured eruptions in real time before. In 2015, sensors detected the first stirrings hours before lava broke through the seafloor. But what the network is recording now suggests something larger may be building. The data streams in continuously, each reading adding to a picture that grows more urgent by the day. And the numbers keep climbing. The seafloor has been rising at rates measured in centimeters per year. Pressure sensors show vertical deformation that follow patterns observed before previous eruptions. By mid-2024, the inflation rate was approximately 25 centimeters per year at the caldera center, though more recent data suggests this rate has moderated somewhat. The caldera continues to swell. These readings place the volcano near deformation thresholds reached before the 2015 eruption. The patterns mirror past cycles, yet each eruption requires slightly more inflation than the last. Scientists interpret this as the crust gradually stiffening, requiring more pressure to trigger the next event. When a volcano inflates steadily between eruptions, it indicates the underground reservoir is replenishing. The crust above stretches and bulges upward as magma accumulates. Eventually, the rock reaches a threshold where it can no longer accommodate additional pressure. That threshold defines the eruption window. Scientists observe that the volcano has reached inflation levels similar to those before its last major eruption. The seafloor has risen steadily over multiple years, approaching a threshold that historically precedes volcanic activity. Yet, predicting the exact moment of eruption remains beyond current capabilities. This uncertainty defines volcano science. Previous eruptions provided patterns researchers now use for forecasting. The 2015 event confirmed that inflation thresholds exist, though they increase slightly with each cycle. Current data suggests the volcano is within the window where an eruption could occur, though whether that means weeks, months, or longer remains unclear. The ground beneath approaches a critical state. Seismic monitoring records between 200 and 300 earthquakes on typical days. Occasionally, counts spike dramatically. In June 2025, more than 2,000 tremors occurred within a single 24-hour period. The quakes cluster around the caldera, with patterns that match sequences observed before previous eruptions. The volcano generates constant seismic noise. Seismometers detect two distinct types of signals. Low-frequency tremors indicate magma moving through narrow conduits, forcing its way upward through semi-solid rock. High-frequency brittle failure quakes reveal rocks snapping under stress as pressure builds beyond what the crust can withstand. Together, these signals tell a story of ascent. The quake swarms cluster along fault lines that ring the caldera. Each tremor releases a tiny fraction of the accumulated strain, but the overall pattern shows stress spreading laterally across a widening area. When quakes begin migrating away from the central magma chamber, it often means the system is nearing a critical state. Previous eruptions followed this exact sequence. In 2015, earthquake counts climbed steadily for weeks before the eruption began. What's happening now mirrors that progression, but the intensity is greater. More quakes, stronger signals, a broader area of deformation. The pattern suggests not just an eruption, but a larger release of pent-up energy. And the tremors continue to spread. Scientists watching these swarms know that each earthquake represents rock failing under pressure. When hundreds of failures occur daily, it means the volcano's internal plumbing is adjusting to accommodate rising magma. The question is not whether the rock will break, it's when. Thermal monitoring reveals elevated heat signatures at hydrothermal vents across the summit. Water temperatures and vent fluids reach levels that indicate active magma intrusion at shallow depths. The measurements show the volcano's thermal output responding to changes in the underlying magma system. The heat signals activity. Chemical sensors detect elevated helium-3 concentrations in vent emissions. This rare isotope originates deep within Earth's mantle and reaches the surface only when fresh magma ascends. Increased helium-3 levels, combined with elevated sulfur and other volcanic gases, confirm that new magma is moving through the volcano's plumbing system. The chemistry reveals ascent. At hydrothermal vents scattered across the summit, shimmering water rises in columns as temperature differentials bend light. Automated instruments record pulses of hot fluid release that correspond with seismic tremors. Each pulse means another batch of superheated water escapes as magma forces its way closer to the surface. The vents are responding. Researchers analyzing these thermal and chemical signatures see clear evidence of magma actively moving upward through the volcano's plumbing system. The heat is not residual warmth from past activity. The helium-3 is not from old cooling rock. These are signatures of fresh intrusion. Magma is rising now. Combined with the inflation data and earthquake swarms, the thermal and chemical evidence paints a consistent picture. The volcano is not merely restless, it is building toward an eruption, and the signs are intensifying faster than previous cycles. Every data stream confirms what scientists feared: the volcano is primed. Researchers who study tectonic stress model how pressure changes propagate through Earth's crust. Theoretical frameworks explore whether volcanic inflation might influence distant fault systems. These models remain largely academic, with limited evidence of significant effects. The question generates debate.
Some scientists wonder whether axial eruptions could affect other tectonic features. But experts monitoring axial emphasize the volcano's activity poses no danger of triggering the Cascadia megaquake. The systems remain separate. Yet both exist in the same tectonic neighborhood. Axial sits atop the ridge where the Juan de Fuca plate forms. Just 200 kilometers east, that plate dives beneath North America along the Cascadia subduction zone. This 1,000-kilometer fault stretches from Northern California to Vancouver Island. Cascadia has been locked for 325 years. It last ruptured in January 1700, producing a magnitude 9.0 earthquake and tsunami. Geological evidence reveals great earthquakes occur here every 400 to 600 years on average. Scientists estimate a 37% chance of magnitude 8.0 or greater in the next 50 years. When Cascadia ruptures, ground shaking will last 4 to 6 minutes. Coastal areas will drop 1 to 2 meters instantly. The threat is real, but separate from axial. Both the volcanic and subduction systems represent independent hazards that Pacific Northwest communities must understand. Axial's eruptions provide scientific opportunities without posing direct danger to coastal populations. Cascadia's locked fault, by contrast, will eventually produce devastation on a scale the region has not experienced in over 3 centuries. Conflating the two creates confusion about actual risks. When Cascadia eventually ruptures, the resulting tsunami will reach coastal communities within 15 to 30 minutes. Towns along Oregon and Washington's coasts face this threat from the subduction zone earthquake itself, not from axial. The volcano's eruptions, occurring at significant depth and far offshore, pose no tsunami risk to coastal populations. The distinction matters for preparedness. Oregon's coastal communities include towns like Cannon Beach, Newport, and Coos Bay, home to tens of thousands of residents. Washington's coastline stretches from Westport to the Olympic Peninsula, where fishing villages and small cities sit within the Cascadia tsunami zone. Evacuation routes lead uphill from low-lying areas, but many roads are narrow and vulnerable to landslides. The Cascadia threat demands serious preparation. Ports in Seattle, Tacoma, and Portland handle supply chains worth over $80 billion annually. A Cascadia earthquake would subject these facilities to intense shaking. The economic impact would ripple nationwide as West Coast trade halts. FEMA estimates a Cascadia megaquake could cause approximately 13,000 fatalities and 27,000 injuries. Over 1 million people would be displaced. Infrastructure damage would exceed $32 billion in Oregon alone. Understanding the difference between axial volcanic monitoring and Cascadia earthquake preparedness is crucial. Axial provides scientific opportunities without posing direct threat. Cascadia represents the genuine catastrophic risk requiring community readiness. The distinction shapes effective preparation. Scientists analyzing axial's behavior disagree on eruption timing. Some point to moderating inflation rates, suggesting months remain. Others note seismic patterns and vent chemistry changes that could indicate shorter timelines. A single day in mid-2025 saw over 2,000 earthquakes, raising concerns among veteran volcanologists. Forecast windows keep shifting.
In December 2024, researchers predicted an eruption before 2025 ended. By spring 2025, some revised estimates to mid to late 2026 as inflation rates declined. But volcanoes don't follow schedules. Small changes in magma supply can dramatically alter timing, and eruption forecasting remains notoriously difficult. Predicting remains imperfect despite advanced monitoring. Over 10 million people live in the Pacific Northwest, concentrated in cities across coastal lowlands and river valleys. Seattle's skyline rises kilometers from Puget Sound. Portland straddles the Willamette River. Tacoma, Olympia, and dozens of smaller cities depend on infrastructure built before anyone understood Cascadia's full threat. The tech corridors face seismic risk. Amazon, Microsoft, and Boeing anchor an economy deeply tied to West Coast stability. Data centers, semiconductor plants, and aerospace facilities sit on ground that will shake violently when Cascadia ruptures. Supply chains connecting these industries to global markets funnel through vulnerable ports. Sarah Chen lives in Cannon Beach, Oregon, 3 blocks from the ocean. Her morning routine includes checking tsunami-ready signs at every intersection. She's practiced the evacuation route with her 2 children until they know every turn by heart.
But Sarah understands practice differs from reality. When you live this close to the water, you think about it every day, she says. At night, sometimes I lie awake wondering if we'd actually make it to high ground in time. Her house sits in the red zone on evacuation maps. She keeps emergency supplies in her car and a packed bag by the door. Most days she avoids dwelling on the fault line beneath the coast, but the worry remains woven into decisions about schools, work, and whether to stay or leave this place they call home. Power grids span the danger zone. Transmission lines cross mountain passes and river gorges where landslides wait. Substations sit on coastal plains vulnerable to shaking and tsunamis. When Cascadia ruptures, the region could lose electricity for weeks. Hospitals, emergency services, and communication networks depend on power that may vanish instantly. Preparedness has improved, but gaps remain. Building codes now require earthquake-resistant construction in new structures, but thousands of older buildings predate modern standards. Unreinforced masonry buildings cluster in downtown districts. Bridges from the 1950s lack adequate retrofitting. Many schools and hospitals may not withstand prolonged shaking. Tsunami evacuation routes exist on paper. For the 10 million people who call the Pacific Northwest home, every tremor reminds them the ground beneath is temporary. The region's forests, mountains, and ocean vistas rest atop a tectonic system that will eventually release centuries of stored energy. Understanding the real threats matters. On Thanksgiving morning 2025, a magnitude 6.0 earthquake struck beneath Susitna, Alaska, roughly 37 miles northwest of Anchorage. It was the strongest to hit the region since 2021. The Alaska Earthquake Center recorded over 6,500 felt reports. Despite lower intensity due to its 70-kilometer depth, the quake was widely felt from Homer to Fairbanks. Items fell from shelves. No major damage was reported. But the earthquake drew attention from seismologists. Alaska experiences frequent seismic activity as part of the Pacific Ring of Fire. The state averages one magnitude 7.0 earthquake yearly and multiple magnitude 6.0 events annually. This quake occurred within normal ranges. Some researchers examine historical patterns. The 1964 magnitude 9.2 Good Friday earthquake killed 139 people across Alaska. Subduction zones can experience varying seismic activity before major events, though predicting foreshocks remains impossible with current science. The Alaska earthquake represents normal background activity for one of Earth's most seismically active zones. Researchers sometimes explore broader patterns. Alaska, Oregon, Chile, the Kurils, and the Philippines all sit along the Ring of Fire. When earthquakes occur in multiple locations, some scientists examine potential correlations, while others note that the ring produces earthquakes continuously somewhere. Statistical analysis has not confirmed systematic global synchronization. Axial showing signs of approaching eruption, a magnitude 6.0 earthquake in Alaska's subduction zone. Regular activity continuing along the Pacific Ring of Fire. These events occur within Earth's most active region, though establishing causal connections remains scientifically challenging. Tectonic activity continues throughout the Pacific. Scientists monitoring Axial interpret data as indicating a probable eruption within months to perhaps a few years. Inflation, seismicity, thermal output, and chemical signatures align with patterns from previous eruptions. Precise timing remains uncertain, a limitation inherent to current volcanology. The eruption will reshape seafloor areas and provide insights into submarine volcanic systems. It poses no direct threat to coastal communities. Previous axial eruptions went unnoticed by ships sailing overhead. But the monitoring network provides unprecedented data advancing volcanic understanding. Even with real-time data from the world's most advanced network, scientists project windows, but not exact moments. The volcano will erupt according to physical processes unfolding beneath the sea floor. The instruments keep recording. The magma continues moving. Somewhere beneath 1,400 meters of ocean, pressure builds toward thresholds defined by rock mechanics. When crossed, the Pacific Northwest will witness a volcanic eruption entirely contained underwater. What matters most is what scientists learn from observing it in unprecedented detail. The question is not if the volcano will erupt. The question is what new understanding emerges and how those insights might help forecast more dangerous systems. In a region where millions face genuine threats from Cascadia, where preparedness requires understanding actual versus perceived risks, every data point from Axial adds crucial knowledge. The monitoring continues.